We present a practical way to generate meaningful features by calibrating the tail categories distribution in a long tail classification setting. This is a joint work with Mark from NVIDIA Toronto, Vineet from IIT Hyderabad, and Makaran from IIIT Hyderabad. Let's begin by understanding the long tail setting in detail first. A dataset is said to be long tail when the majority of the samples are from a few head classes and there are very few samples from the tail classes. In the hypothetical scenario shown, the data points available for dog class are extremely low compared to that of the cat class. Irrespective of the fact that both are extremely cute, when trained with any state-of-the-art method, the dogs would stand no chance against the cats on the prediction front. It is noteworthy that real world is inherently long-tailed and not an artificial construct. As a result, almost all the time the datasets collected from the real world are long-tailed. These kinds of datasets are generally denoted by their imbalance factors, which is a ratio of class with the maximum number of data points to the class with the least number of data points. This naturally brings up several questions like, how would it affect the accuracy of the prediction? What kind of real-world consequence would such a dataset have? Ultimately, why studying long tail is important. Let's take the same example of cats versus dogs. Say there are equal number of data points for both the classes. When we train an MLP using it, the decision boundary looks something like this, and the test accuracy is 100%. Note that this is a toy dataset, which is the reason for the perfect score. Let's randomly remove data points from the dog class now and make the imbalance ratio equal to 100. Then retrain the model based on it. When we look at the decision boundary, it is clear that network is struggling to recognize dogs correctly. Despite this being a toy dataset, the test accuracy plummets to 50%. When talking in terms of dogs and cats, this issue might not be very pressing. But if we replace the dogs versus cat scenario with male versus female, suddenly the gravity of the situation is much more evident. Remember, this is when we restrict ourselves to just two genders. When we take into account the other genders, this issue worsens rapidly. This problem gets even more dire when we talk in terms of deciding which vaccine to prescribe based on a long tail data. Suddenly, it's more of an ethical issue rather than just a cuteness competition. This is why it's important to study and address the long tail in the datasets. While there exist several ways to approach such a scenario, we explore a direction that attempts to generate meaningful features by calibrating the tail categories distribution and making it balanced. Let's dive deeper into the proposed method now. Consider a dataset with three different classes which have a long tail distribution. Say class 1 is the head and class 3 is the tail. As shown in the figure, if you train based on the so-called dataset as it is, we have faulty decision boundary that classifies class 3's validation samples as class 1. The samples of this dataset have a distribution that is not Gaussian, and this makes it difficult to understand and calibrate them. So we need to make it resemble a Gaussian distribution in order for us to generate samples using them. But before we proceed further, first we compute the class statistics, namely mean and variance for each class separately. These will come in handy later. Now we use a 2K transformation mapping in order to make the distribution of the classes closer to Gaussian distribution. Now using the features that resemble a Gaussian distribution, we do nearest neighbor search in order to find the classes based on which we can generate the new samples. More precisely, we first decide how many samples are we going to generate for each training data point so as to balance the dataset. Then we take one such training data point and find nearest neighbor categories by comparing distances to the centroids of all classes. The intuition behind choosing the nearest classes is that classes that are close to each other in feature space would share similar features. The number of nearest classes to take into account is a hyperparameter we play with in our paper. Then we take the corresponding statistics of the selected classes that we calculated earlier and average them. We call this the calibration step. Note that there is an alpha added to the averaged value. This basically controls the spread of the generated samples. Alpha is also a hyperparameter that is dataset dependent. For simplicity of sampling, we construct a Gaussian distribution based on the calibrated mean and variance from the previous step. Then we draw a sample from this distribution. Recall that until now, we have generated new samples based on just one training data point. This may not be sufficient to balance the dataset. Therefore, we repeat the steps of picking a training data point, finding the nearest neighbors, getting calibrated statistics, and sampling from the calibrated distribution until the dataset is completely balanced. We use this new balanced data to train a final classifier. Ideally, this should provide a better decision boundary that encapsulates and generalizes to unseen data points from the validation or test sets. We tried out two different variations of the train data generation protocol. Typically, when we generate once and use that to train, we call it train tailcalib. But when we generate new samples at every epoch and train using them, we call it tailcalib X. The X here indicates the multiple generation steps instead of one used in tailcalib. Let's talk numbers now and see how our method performs in comparison to the existing literature. First, let's revisit the toy example which we studied at the beginning. When the imbalance ratio is 100, the test accuracy becomes 50%. How does our method perform in this scenario? The newly generated samples based on a method have pushed the decision boundary back, effectively increasing the test accuracy of the dogs to 99%. This is a proof of concept that our method works. Now let's benchmark on more complex long-tail datasets. On C500 LT dataset, firstly, note that cosine CE training paradigm is superior to CE, which is cross entropy, and in fact outperforms several gross leaveating-based methods. Cosine CE plus tailcalib X outperforms all previous works, ignoring distillation. In fact, it achieves performance close to CBD, especially on imbalance factors 150. That trains two networks, a teacher and students, and benefits from the advantage of ensembling. Finally, applying tailcalib X on top of trained CBD model results in further performance improvements of 1 to 2%, notably for imbalance factor 150. Apart from becoming a soda on C500 LT, we also demonstrate that tail calibration is orthogonal to and can be combined with other works to yield additional improvement. On mini ImageNet LT dataset, tailcalib X outperforms all previous work. As compared to the cosine CE baseline, not only does it improve the accuracy for tail classes by over 20%, we also see performance improvements for both the middle classes and head classes as well. Surprisingly, CBD performs worse than the classifier retraining, that is CRT. Hence, we omit evaluation of tail calibration as applied to a backbone trained with CBD. If you have a long tail or imbalanced dataset and need a quick fix that boosts performance, then try out a pip package. Just use the command pip install tailcalib. It supports both CPU and GPU acceleration for convenience. Using it is extremely simple. All you have to do is install and import it like in line 3. Then initialize it with either NumPy or PyTorch depending on your use case, like in line 6. Then input the imbalance data along with its labels, like in line 4. For much more advanced use cases, take a look at the pip package documentation page. Here are some useful links. Don't forget to check out our Colab notebook to play with the method. If you are interested in deep learning research which involves long-tailed or imbalanced dataset, we recommend you to take a look at long-tail bus to learn about the recent training papers in the field. Thank you.